Hello and welcome to Buildings of Tomorrow. My name is John Lester and today's episode is another buzzword buster. So if you haven't heard one of these episodes from us in the past, they're a slightly longer format, and basically we pick one of the topics that we discuss within our normal episodes, and we just have a look at a lot of the terms and a lot of the phrases that you hear in the industry and run through with an expert to give a brief description and a definition of those terms. There are so many things changing in our industry. We hear so many terms that perhaps we don't have a full understanding of what they mean. So that is why the buzzword buster exists. And today we are talking about hydronics. I'm joined by Chris Kopp, who is an expert in HVAC theory and hydronics. Chris, thank you very much for joining us.
Hi, John. Thank you very much for having me in this episode.
It is always a pleasure, recorded from home. We keep charging no matter what happens outside, right? Perfect. So today is a buzzword buster. As I mentioned, hydronics is the topic. We're going to dive straight in. We've taken a slightly different approach here. We want to keep it a little organized because a lot of these terms really do refer to each other or related to each other. So we're going to start and run through a bunch of different hydronic buzzwords. And where we're going to start is at a phrase or an acronym that we hear a lot in the industry, which is PICV. Chris, what is PICV?
So PICV stands for Pressure Independent Control Valve. And this already explains a little bit what it's all about. It's an approach for a control valve that has been launched a couple of years ago and is now steadily finding its way into the applications, into the hydronic circuits. And as the name says, it is a control valve. So that's one key part of it, as in any other control valve. But then there is an additional differential pressure controller that basically surrounds the control valve and makes sure that pressure changes, fluctuations in the hydronic network do not get to the control valve. So it kind of decouples the control valve from the surroundings, and by that we can achieve more stable control. And then the third component is that in these PICVs, pressure independent control valves, we also have the possibility to limit the maximum flow, and by that we are already one big step in the direction of hydronic balancing.
Perfect. And you mentioned there the maximum flow. That's actually the next word we had on the list, Vmax.
Yeah. Okay, so the maximum flow is, as I said before, something we can set on such a PICV. It's a mechanical setting, and it ensures that we get the right maximum amount of flow, and by that we do hydronic balancing. So if the installer sets that maximum flow on every PICV that he puts into the hydronic circuit, the system is already balanced. And it's much less effort to do it at this point in time than with traditional valves to go back and do it basically when the total installation is finished. And that's a big also time-saving effort, as we have seen in many projects.
Beautiful. Thank you. So we have the next word, which is also a PICV related one, probably on the other end of the scale to a certain extent, a delta P min.
Yes. So as the term says, pressure independent refers to this differential pressure controller, which is a mechanical setup within this complete control valve. And for this differential pressure controller, it is necessary that the pump provides a minimum pressure. This is kind of the driving force then of the differential pressure controller. And this is basically, in addition to the maximum flow that needs to be calculated and considered, is the other key value that needs to be taken in consideration. And the delta P min is what we have to make sure that it is always available at this PICV, because then it works properly. If the pump pressure puts less pressure on the PICV, it basically defaults back to a standard, normal, or KVS valve. And then you lose the benefits of this independence of the pressure situation surrounding the valve.
Right. So the delta P min is the minimum system pressure that has to be applied at that valve at that point in the system for it to be able to operate as a pressure independent control valve.
Absolutely.
Beautiful. So, pressure-independent control valves, we just had a look at two of the key topics that go along with that. Let's look at the more traditional valves that you mentioned before, a KVS valve.
Okay, so today we see more and more PICVs, but that doesn't mean that the traditional KVS valves or standard globe control valves or also ball control valves that work in this pattern are no longer needed. They still have their applications where they are suitable, and therefore it's important to know what is a KVS valve. And KVS basically stands for the maximum flow such a valve can handle under predefined condition. And the predefined condition is that the KVS is a volumetric flow in cubic meters per hour, and it is defined at a pressure differential across the valve of 1 bar or 100 kilopascal. So it's a clearly defined setting that helps then to compare different valve types or products against each other and make the proper selection.
Perfect. Now let's have a look at a couple of key terms or valve characteristics that we might see with a KVS valve, similar to what we did with a pressure-independent valve. V100.
Yes. V100. That's a term that you could also apply to a PICV, but it's mainly used with KVS, and it's really the 100% volumetric flow, you could say. And this is derived from the equation that considers the power that we have to provide to a consumer and the decisive temperature difference that is needed at this consumer. And out of that, we can figure out how much water do we have to be able to handle with this valve. And that's what's called V100 for this KVS valve.
Okay, beautiful. And related to that to a certain extent, the delta P V100?
Yes. As you said, it's related because it also says V100. So it's the delta P, the pressure differential that we would like to have at this valve when we have the nominal flow derived from the power equation. And it's important that we consider that with the KVS valves in order to reach a good controllability of the system.
Amazing. Now, one of the other parts that we see when we're sizing KVS valves, one of the important parts is to understand the valve authority or the PV of that KVS valve. Can you give us a bit of an insight into the valve authority?
Yes. So the valve authority, P index V, is an indicator of good controllability, you could say. And as a rule of thumb, we say it should be 0.5 or a little bit higher. And in other terms, it means that the resistance across the valve that we basically put into this hydronic circuit by selecting the appropriate valve size has to relate to the part that the valve wants to control, and this part we call delta P MV, and that's another term, but it nicely fits now. It relates to that, and it just means that the resistance across the valve should be equal or greater than the resistance in the variable flow part that is controlled by the valve. And this variable flow part is then called delta P MV. And you might wonder, what does MV stand for? It comes out of certain standards and norms, and it's derived from a German term. It's called Mengenvariabel, which in English means variable flow part.
Perfect. Thank you. You mentioned just then variable flow, and I think that's a really good time for us to take a step back from the valves as they are, the individual components there, and look a little bit more at the system. So what is variable volumetric flow?
Okay. So variable volumetric flow, I think in today's situations is key, because when we set up hydronic circuits from the producer across the distribution all the way out to the consumer, we really want to have variable volumetric flow, meaning we only want to move as much water as it is currently needed through our system with the pumps. And if we achieve that, then of course the whole system becomes more efficient because we don't circulate unnecessary amounts of water, which then needs a lot of electrical power, and also we don't have heat loss in case of a heating system or heat gains into our network in case of a chilled water system. So volumetric flow is basically the guiding idea when we set up a state-of-the-art hydronic network.
And that volumetric flow, or the variable volumetric flow,
should be variable, exactly.
Should be variable, and that's the comment I was trying to make, was that perhaps at a different time in our industry, or before variable flow, volumetric flow was consistent, this the static volumetric flow, or constant volumetric flow was the norm, correct?
Yes, it was often done this way or used because it ensured that we had warm or cold water available out at the different consumers whenever there was a need. But I think today that's less of a critical topic, because with modern building automation systems, there is so much information available that it's possible to derive and decide when do we need what type of flow in which locations, and you can handle it from there. So it's no longer necessary to bring out, let's say, cold water to an air handling unit that is at the other end of the building, just to make sure that in case cooling appears from the control side, we are ready to go. We can achieve that today in most cases by gathering information from the system setup and analyzing that in the building automation system, and then basically decide what needs to be done at any given time in the system.
Right. So we're better at collecting information, and then we're more able to react to that and make changes within the system in enough time to be able to absorb those requirements when they come along, so that we don't have to plan for and always deliver the highest demand situation.
Yes, exactly.
Beautiful. So still looking at the system perspective, maybe we'll zoom in just a little bit to understand and look at a couple of terms that we hear around the different circuits and the requirements. It's something that you mentioned before, and maybe the next word or phrase that we'll look at is hydronic balancing, because that came into the discussion a little bit earlier.
Yes, hydronic balancing is a term that is often heard and also required in specifications and things like that. But what we find, unfortunately, it's very often not done properly, because if you want to do it in a big system in a proper way, it needs time, and people are always crunched for time. So that's one of the things that then is left out, and people then just hope and cross their fingers that we get enough warm water or enough cold water to our consumers. And if that happens, nobody will make any bad comments about it. But what we then find is very often we lose on the energy efficiency side. So yes, the room gets warm. Yes, the chilled water goes out to the air handling unit in a sufficient amount, but it's not in the best energy efficient way. And that's why hydronic balancing is an important key part. And it can be done in two ways. Traditionally, it was done in a way that we would call static hydronic balancing, meaning setting the maximum flow with a separate balancing valve at each consumer circuit, and by that ensuring that they get the proper amount of water. But because this is a one-time setting at basically startup or initial installation, it is correct at this point of operation. But we all know our systems are dynamic, and most of the time we have 50, 60, 70% of water that is needed. And then these static balancing elements have some influence on the overall system behavior. And it can very well be that all of a sudden, some consumers get more water than they would like to have. You can control that, but some other consumers might get not enough water, and then we have a problem. And it has to do with the dynamic behavior at different operating points. And because of this, the trend today is moving towards what we would call dynamic hydronic balancing. And this can be achieved, for example, with the PICVs that we talked about before, because there you also set basically the maximum flow comparable to the static balancing. But because now this PICV is separated from the changes in the hydronic network, the pressure changes and so on, we have a much more stable control. And that helps to achieve balanced situations also during dynamic situations. So you always have a balanced system then at 50% of load, at 70% of load, and not only clearly and fully balanced at 100% of load, like this was done and has been with static balancing in the past. So here again, the trend is to move towards hydronic dynamic balancing, and this can be achieved, for example, utilizing PICVs.
Okay, so we used to use a single snapshot, 100% loads and 100% demand to test to make sure that our system operated as designed. But obviously, yes, as soon as that situation changed, the demand changed, the pressure within the system changed because of that demand change, or we used variable speed pumps or something like this, then all of a sudden that snapshot was not always accurate.
Yes, exactly.
And this dynamic approach means that no matter what happens within the system, we're able to deliver the expected flow to those individual consumers as they've been designed.
Yeah, exactly, because then the cross influence that can happen amongst consumers is eliminated.
Perfect. So let's have a look at a couple of different circuits, because we've talked about valves, we've talked now a little bit about the system, but the circuit itself is really the all-encompassing part of this individual consumer. So not just the valve itself, but the coils and any other actual temperature or energy delivery device into the airflow, etc. We have two different circuits here on my list. So we'll go one at a time, and you could give us a little bit of an explanation. That would be great. So the first I have is throttling circuit.
Yes. So a throttling circuit, basically the term says exactly what it's doing. You have a valve in a pipe, and it just shuts off or lowers the flow by closing off. So it throttles the flow in this entire circuit, and we use that a lot in situations where we want to supply a variable flow to the consumer, and we want to ensure that we always get the same supply temperature to this consumer. For a good example for that is in a chilled water situation, when you have to provide cold water to a cooling coil, not only for cooling the air, but also for dehumidification of the air. Then we have to make sure we always get really very cold water, more or less, from the flow part to that coil in order to make the dehumidification happen. And so the throttling circuit is a proven circuit to use in situations where we want to have variable flow, but always a steady supply temperature to our consumer. And it also is a good circuit to utilize the PICVs that we talked about before, because the PICVs in general are two-port valves, and because we just put a valve into one pipe, a two-port valve is sufficient.
Mm. Yeah, that was the perfect summary, I think. So a valve to deliver the same supply temperature, but to regulate the flow.
Yes, yes.
And the next one I had was injection circuit, which I'm having a guess here is perhaps the other way around to a certain extent.
Yeah, it's a little bit a different setup. And when we talk about injection circuit, we have to differentiate it. Is it an injection circuit with a two-port valve or a three-port valve? And to be honest with you, my hope is that a couple of years from now, when somebody says injection circuit, it is clear it's one with a two-port valve, because this setup is the energy efficient setup, because the injection circuit provides a constant flow across the consumer and controls the power or the capacity with changing the temperature spread. And adjusting the temperature difference is done by injecting, in a heating circuit, for example, more or less hot water from the production side into the continuous circulating water stream across the consumer. And the two-port valve is then in the supply line from the production side, which means there again, we are with variable flow in the long pipes from the production all the way out to our consumer. And so that's again a situation that we want to see more and more in the future, either throttling circuits as discussed before, or then injection circuits with two-port valves.
And these two circuits, by using two-port valves, these are the preferred approach, because if we use a three-port valve, we're pumping water around in circles for no particular reason. Is that correct?
It's correct in certain applications. So that's why, for example, the diverting circuit and the injection circuit with three-port valves, they should go away, right? I don't like to see them anymore in new plannings, for sure not. And also in existing situations, people should really think about to convert them to throttling or injection circuits with two-port valves, which is very easy. The mixing valve, the three-port valve, still has its applications with the traditional mixing circuits. There, it still makes a lot of sense in typical, let's say, heating applications, where you have your distribution and your consumer circuits in the boiler room, in the heating plant room. There they are still applicable, and they are also energy efficient under these considerations.
Okay, perfect. Thank you. So let's get away from the circuits now. The next term that I have on the list is proportional laws and affinity laws. Could you give us some insight into those?
Yes. So proportional laws, as we, let's say, call it more in the German-speaking countries, or let's say in Europe, or affinity laws, as they are called in English-speaking countries, are basically laws that are derived from the fluid dynamics theory. And these laws apply to our hydronic setups, meaning our water-based circuits for heating and cooling, but they also apply in the same manner to our air streams in the ductwork. So these fluid dynamics laws we can apply with the medium that we normally work with, either water, cold or warm, or then with the air that we run through the building. And they are very important because they have a big impact on energy efficiency. And let's say the main one, or the key one, is the proportional law number 2, or the second one, because it defines that the resistance in our hydronic network changes not directly proportional, but it changes by the square compared to the volume flow that we run through this network, which I think is very obvious that if you only run, for example, half the volumetric flow to a pipe that was designed to handle 100% of this flow, the resistance that you get on the walls of these pipes or so goes back rather drastically, because your flow speed is much lower and you have a lot less resistance. And the fluid dynamics theory says that this resistance goes down by the square. So for half the flow, it means we only have to overcome a quarter of the resistance that we had to overcome at the design conditions. And that, of course, is a big change, and it is a very, let's say, fundamental law in our hydronic circuits, because then based on that, also the power consumption goes down dramatically. And here the theory says it goes down by the power of 3, which is a little bit too optimistic, but in a lot of cases, it goes down dramatically by more than the square or close to power of 3. So that's why we should really focus on these proportional laws, and they are basically the reasons why we have variable speed drives, why we have EC motors and pumps and fans, that we can then control the speed to really work with these laws and get as much as possible out of it.
Okay, perfect. Chris, thank you so much. We've covered a huge amount of different terms, whether they're part of choosing, selecting, and ensuring that we understand correctly the valves that we're putting within the system, the circuits that help make up that system, or the system itself, how we describe it, and how we look at the way that we control the flow and the different approaches that we have in controlling the pumps that deliver that flow and that pressure. Thank you so much, as always, for joining us. We very much enjoy it when you visit me. I get the feeling that we probably have another one of these buzzword busters in us when we want to talk about other components of the HVAC systems.
Yeah, but I think there is more to discuss.
For another good buzzword buster, for sure.
Yes.
So thank you. Anytime. Thank you again, Chris. And thank you to all of you out there for listening to this episode. Please feel free to share, like, and comment on this episode. Subscribe to us on whichever channel you're listening to us right now. Remember to share. And as always, we very much appreciate your time in joining us, and we look forward to seeing you again soon. Thank you.